start record. Yes. Okay, we were talking about these matrices A and B, partition of matrices. So if A1, A2, A3, A4, and B1, B2, B3, B4 are real numbers, we just multiply it like this. But still, we can multiply this way whenever this multiplication is possible for matrices. So for example, let's compute this as an example. So A1 plus B1 plus A2 plus B3. Let's compute. A1 is 1, 2, 0, 1 times B1 is 1, 1, 1, 2 plus A2 is 3, 1 times B3 is so not B3 is 4, 5. 4 and 5. Let's multiply this. This is the first matrix is 3, 5, 1, 2 plus 3 times 4 is 12, 15, 4 and 5. And when you add them up, what do we get? 15, 20, 5 and 7, right? I hope it's correct. Okay, next, A1, B2 plus A2, B4. A1 is 1, 2, 0, 1. B2 is, what's B2? 3, 4, 0 minus 1. 3, 4, 0 minus 1. And A2 is, what's A2? 3, 1. So, yes, 3, 1. B2 is 2, 1, like this. Let's multiply this, these matrices. It is 3, 4 minus 2 is 2, 0 minus 1 plus multiplication of these two matrices are 6, 3, 2, 1. And when you add them up, it is 9 plus 5, 2 plus 0. Okay, next, A3, B1. A3, B1 plus A4, B3. That is A3, what's A3? A3 is 1, 2. B1 is 1, 1, 1, 2. A4 is just 4. B3 is 4, 5. And that is 3, right? And 5. Plus 16 and 20. And the result is 19 and 25. One more. Finally, A3, B2 plus A4, B4. A3 is 1, 2. A4 is 4. B2 is 3, 4, 0 minus 1 is here. And B4 is 2, 1. And you multiply this a little bit long, but it is good. It is 3. 4 minus 2 is 2, right? Plus 8 and 4, which is 11 and 8. So this matrix, let's call this matrix C. This matrix C is equal to first entry 15, 20, 20, and 5, 7. It's like as first entry. And the second entry is this guy, 9, 5, 2, 0. And the entry here is 19 and 25. And here is 11 and 8. Well, you should check that this is equal to AB, A times B. I leave this to you to check that that's the product of A and B. So the main objective of this example is that instead of multiplying two matrices together, you can partition them and then multiply it this way. Sometimes it's easier. If there are many zeros, for example, you can multiply it that way. Okay. Well, in general, you can also generalize this partition, but I will not write the formal definition of the partition matrices. It's exactly the same. So when you have a let's say A11, A1n, AM1, AMN, and B as B11, B BN1, B11, B1R, BNR, for example. So if you have two matrices like this, when A1, A11, whenever these entries are number scalars, how do we multiply? We just multiply it in the usual way. But if they are matrices, you can multiply in the same way, as long as this product is multiplications are possible. That's the partitions of matrices. So this A times B is equal to this A, B, I, J. The same formula holds. Same formula holds. So, or same multiplication formula holds for partition matrices. Okay, we gave examples above. And one more thing is, for example, if we have a matrix A11, A1n, and AM1, AMN, if you multiply this matrix by something like R1, Rn, the result is, so suppose this everything is real number or complex numbers. This is remember how it is A11 plus times R1 plus A1 and Rn, and finally at the end AM1 R1 plus AM N Rn, or this is, or we might write it like this: R1 times when Ri's are real numbers or from the fields, Aij's are from the field. This is R1 times A11, AM1. So the first part like this, and then R2 times A12, AM2, etc. And finally, the last entry will be Rn times A1n, AMN. Namely, this multiplication is, so, well, we say this. So this is A1, 1. Let me change this color first. This is the first column, the second column, etc. This is the last column. This is the first column, second column, and the last column. So this product is we say that this product is the linear combination of these columns. So that in this case, the product this is not A times, let's call this B. A times B is the linear combination of is a linear combination of columns of A. Okay. Next. Next, diagonal matrices. So suppose, so let A be a square matrix, be an n cross n matrix. So if Aij is 0 for I is not equal to j, then we say that A is a diagonal matrix. So what's the diagonal matrix? So so that A is, so A11 is possible, but A12, when you have A12, 1 is different from 2, so it is second entry is 0, third entry is 0, etc. Here A21 is 0 because I is not equal to j, and A22, etc. And finally, ANN is here, and all the entries other than the main diagonal are 0. So we also write this as the diagonal matrix, diagonal A11, A22. Let me write also one, okay, ANN. So for example, so when we say diagonal matrix, let's say 1, 2, 3. So this is a 3 by 3 matrix, 1, 2, 3, and all the other entries are 0. Okay? Or you may have the diagonal matrix, for example, 0, 1, 1, 1, 0. It is this first A11 is 0, all the other entries are 0. Here is 1, here is 0, and the rest is 0. Right? Diagonal 0, 1, 0. And of course, diagonal 0, 0, 0, if everything is 0, it's a 0 matrix. Every entry is 0. Good. Every entry is 0. And if you look at this diagonal matrix consisting of all the same numbers, let's say A, oops, A, n of them, these are A's, it is A, and the rest is 0, like this. Let me write like that, this way. It is, you can take A outside. You can take A outside. It is 1, 0, 0, 0, 0, 1, 0, 0, 0, and 0, 0, 1. So it is A times identity matrix. I don't specify the size, but it's let's say if there are n A's, it is In. Sometimes we write I. In general, we write I, but sometimes we may write In to denote the size. There is a chat. What it says? Can a value in the main? Of course, a value in the main diagonal can be 0. Can be 0 or non-zero. It doesn't matter. We just give an example here. If everything is 0, here is first and the last one is 0. Okay. Triangular matrices. Triangular. Some microphone is open on. Please turn it off. Triangular matrix. Hey, dear friends, can you turn the microphone off, please? Yeah, good. No? Still somebody is talking. Please mute. How do I do this? Okay. A triangular matrix. A square matrix. Square, let's say n cross n matrix. Let me say it. Oops. The square n cross n matrix. A is called upper triangular. If it looks like a triangle, upper triangle. If Aij is 0 for all I is greater than j. Namely, if A is in this form. So we have A1, 1. So 1 is equal to 1. But if A2, 1 is 0 because 2 is bigger than 1, etc. A2, 1, A2, 2, and then the rest is 0 here. A1n, A2n, and ANN. So everything below the diagonal should be 0. And along the diagonal or over the diagonal is it may be 0 or it may not be 0. So this is an upper triangular matrix. In particular, diagonal matrices are upper triangular. Diagonal matrices are upper triangular. Well, we said upper triangular. So the opposite, what's the lower triangular, right? Let's see. Well, I can mute everybody, but I should have done from the beginning. I use iPad and computer, so I have to change it. I don't want to change it. If it is too annoying, just let me know right there, and I will mute everybody. Okay. I have to change the screen otherwise. Okay. Let's see. Lower triangular. How about lower triangular matrices? That is, A is lower triangular. if aij is 0 for all I is this time is less than j. So namely, everything about the main diagonal is 0. So that this A is, maybe I should have called B. Anyway, A is A1, 1. Here is A2, 2. And A N, N. Here is A2, 1, etc. You may have something, but here about the main diagonal, everything should be 0. Now, the question, how about diagonal matrix? Are lower triangular also. So it's like a two sets. A set of upper triangular matrices. Let's say, think it as a set, upper triangular matrices, and the set of lower triangular matrices. And this intersection is both upper triangular and lower triangular, so it is diagonal matrices. So a diagonal matrix, both upper triangular and lower triangular. Okay. And of course, if a matrix A is upper triangular, then it's, yes, everything is square matrix now. When we are talking about upper triangular, lower triangular, everything is square matrix. Otherwise, it doesn't make sense. There's no main diagonals. There's no main diagonal. If A is an upper triangular matrix, then its transpose is lower triangular. Okay. If A is lower triangular, then its transpose is upper triangular. That's also true. Next, so let's see. Let me give one example of this. If A is an easy example, let's say 1, 2, minus 1, 0, 1, 1, 3, 0, 0, for example. This is an upper triangular matrix, and its transpose is 1, 2, minus 1. This is 2, 0, 1, 1, 0, 0, 3. It's a lower triangular matrix. And if A, B are upper triangular, also this is also true for lower triangular, but just let's write for upper triangular. Upper triangular matrices, then let's say A times B times B is also upper triangular. So namely, if you add two upper triangular matrices, or if you multiply by a scalar matrix, still they are upper triangular. Also, so i.e., this is a linear combination of matrices, linear combination of upper triangular matrices is upper triangular. Oh, by the way, what is a linear combination? I did not say that. So, so let A1, AK be matrices of the same size. Same size, and let let's say C1, CK be elements from the field. Field is real numbers in general, as we said. Then a linear combination of a linear combination of A1 and AK is C1 times A1 plus C2 times A2 plus CK times AK. Linear means, just like in the calculus, linear means the degree is 1. So you don't have A square, A1 square, A2 square, or their cube. So degree 1 polynomial, right? Degree 1 polynomial is just X. You have just X, Y is only 1. They are linear. So, so in this linear algebra, later we will see, this will be important later. When we will talk about, vector spaces, these properties will be important. Okay, next. So here is another example. Not example, but definition. I should have done this from the beginning, that I should mute everybody. Okay, I will do it next time. Here's the definition. So a matrix, a square matrix, more precisely. So birileri bilgisayar açıp şey yapıyor herhalde, ha? Gidiyor dersteymiş gibi. A square matrix A is called symmetric. There should be two M's here. Symmetric if its transpose is equal to itself. It's called it is called skew symmetric. Or it's also sometimes it's called anti-symmetric. It's the same thing. If its transpose is equal to the minus identity, minus A, sorry. And you can check that if A transpose is the minus identity, then the main diagonal is 0. The main diagonal. So every entry is 0 along the main diagonal. So let's give some example. Example of a matrix. Let's say 1, 2, minus 1, 2, minus 1. Here you may have 5, 0, 0, 4, for example. This is a symmetric matrix. Because when you take its transpose, you get the same matrix. So I choose that way. And if you look at this matrix B, let's say 0, 2, minus 1, and minus 2, 0, let's say 4, minus 4, and 1, 4, 0, this is skew symmetric. Okay, these are skew symmetric matrices. How much? Let's see, somebody, there is a question. Saz sesi geliyor. Evet, gelsin, saz sesi iyidir ya. Şimdi kayboldu. I have a little bit more. Perhaps we should, how much time do we have?
We have 5 minutes.
5 minutes. Then let's finish here, and then I will start in 5 minutes. After 5 minutes, let's start another lecture, and we will continue something like 20-25 minutes, and then we will finish the lectures. Okay? Let me finish here. After 5 minutes, like now it is 3:05.
Okay.
Yes. Okay, let's finish. How do we finish? Finish. End meeting.